Hi. Um, can you believe that this is the start of the fourth week of online instruction? This is my 13th video lecture. Um, we have 3 more weeks to the end of the semester, and then we'll have finals week. I'm still trying to figure out how to do a test on the 16th of April. So that's in 2 weeks. That's just prior to the week before finals. So that's the Thursday of the week before finals. So that'll be in just under 2 weeks. Okay. So be aware of that. You really need to watch the videos. You really need to watch all the videos. You really need to watch all the videos. Okay. Way too many questions at the end of last week. Well, actually, starting at the start of last week, saying, so which video is that in? Where in that video is that? If you'd watched the videos, you would know where it was, and you would know which video it was in. So, watch all the videos, all the videos, okay? Most of the code is given to you. Now, you will get your last programming assignment tomorrow. So, that assignment will be a linked list. It will be a linked list that's kept in order. I haven't decided what the application data is yet for that list. It will be simple only because the code for the linked list is the important part, not the code for the application data. It's the same as the stack and the queue. The code for the stack and the code for the queue are the important parts here, not what's stored in those nodes, okay? So the applications that I've been giving you are just example applications, toy applications, and the linked list will be the same. But the key is the code and the algorithm for what you're doing with the linked list, with the stack, with the queue. So in the linked list, we need insertion and we need removal. So we've got to be able to insert data into the linked list, remove data from the linked list, print out the linked list, tell if the linked list is empty or not. Find something in the linked list and retrieve its data. And that's about it. I think that's all the member functions you need. So today I'm going to go over insertion in detail. And so what you'll want to do is pay close attention. I'm going to mute the video, and then I'm going to share you my PowerPoint slides. And then we are going to go through these step by step. Okay. Now, linked list insertion has different cases, and each case requires different code. Each case can be identified by using a sequence of ifs and elses. Now, the order in which you check for each of these cases is important because you have to take care of some cases before others. There's sequence involved here, right? So you want to get the sequence right. So the first thing we're going to do is work through that ordering, and then we're going to work through some specific examples of insertions with the code that implements each of those cases. And so the example data that I'm using isn't the important part. The actual code is the important part. Okay, so here are the cases. You've got a normal insertion case, and that means you're just inserting into the middle of an existing list. New data comes in, you have to walk part of the way through the list to find the spot that you're going to insert. Okay. There's an empty list case. You don't have anything in the list. Head is null, and so you have to make sure that head is updated correctly. Insertion before the head. So you've got a list, but your new data comes before any of the data in the list. Okay, so that means not only do you have to insert the new data, but you have to also fix head. So head has to be updated correctly. After the end of the list, so our test pointer is going to walk off the end because the new data is greater than everything in the list. Okay, so we're assuming our list is ordered from least to greatest. Okay, so if the data is less than anything in the list, it goes before the head. If it's greater than anything in the list, it goes after the end. We can't tell those until we search. Okay, and then there's sometimes an application-specific special case for a duplicate key value. Now, we don't know if this is allowed or not. And so when we're building linked lists, we normally just ignore this case. Okay, allowing there to be multiple keys of the same value. Now that key value might be a string compare, it might be last name, first name, middle initial. String compares, it might be a numeric value. It's hard to say. Okay, so what's the order? So normal, before the head and after the end, all require comparing the data to be inserted to the data that's already stored in the list. And so that new data, that data to be inserted, gets compared to things that are already in the list. Well, if we don't have a list, then we can't do that comparison. And so we really need to handle the empty list first. So otherwise, you know, if we attempt to compare the new data to anything from, you know, anything that has to do with the empty list, we're going to get a seg fault. And that's because we're going to use the null value that's in head. So this empty list case goes first. Okay. So we're going to ask if we have an empty list. Normal before the head and after the end can't be identified until after we search for the insertion point using a simple while loop. And we're going to use two pointers, a test pointer and a previous pointer. So the test pointer is going to start off at head. The previous pointer is going to start at null. And then we're going to run the loop and compare data until we either walk off the end of the list or we find where we need to insert the data. So in either of those cases, or excuse me, any of these three cases, okay, you're going to have to find the insertion point with the while loop and then take care of the cases. So that means we're going to else off that if statement, the if empty list, else we're going to search with a while. Okay. Now the while loop finishes either having found a node whose data is greater than the data to be inserted, the new data, or it's walked the test pointer off the end of the list. Now, since test is going to be null if it walked off the end of the list, we should handle the after the end case immediately after the while loop finishes. So that one's going to be easy to pick off. If test is null, we know we walked off the end of the list, and we know that we want to insert after the end of the list. So that's our first test after the searching with the while loop is done. So if the test is null, okay, or if test pointer is null. Provided test is not null, we either have the normal case or the before the head case. The before the head case has two different ways to determine it. That is, if test is equal to head or if previous is null. Either one of those work. You don't have to check both. All you have to do is check one. So you want to set up your if statement to say if test is equal to head, or you can set up the if statement to say if previous is null. Previous is null is just a little bit cleaner and a little bit easier. So I'm going to use previous is null. So if, you know, here's what we really have. We've got the order now. We know how we're going to do it. So we're going to say, is it empty? And then we have the code for the empty. Else search with the while. And then under that, after that while loop, still in that else, if the test is null, we have the code for after the end. Or if test is null, code after the end. Else if previous is null, code before the head. Else code for the normal. Okay. So let's start, you know, with the first thing that we have to decode. Is it the empty case? So if is empty, remember we have the method in our linked list class. I'm going to pause the presentation here just for a bit. So I'm going to stop the share. So I'm going to pause and I'll be right back. I want to get something to drink because my throat's getting a little. Okay, I'm back. Just a little bit of a scratchy throat, nothing to worry about because I've been in isolation now. This is day 19. So I'm going to share back the PowerPoint slides and we'll continue on with the slideshow. Okay. So just to remind you, we're starting with the empty case, the first case to decode. We've got head equal to null. It doesn't have an address in it. Head is null. And we've got some new data to insert, and that new data is Dallas at 475. So Dallas is indeed at 475 feet above sea level. We're going to insert Dallas into the list. So the first thing we need to do is get some space for Dallas. Remember, new data is the parameter to our insertion function. So our insertion method. So we're saying insert new data and, you know, something like my list dot insert new data. And this is the code in that insertion routine. So if it's empty, which it is, okay, then we're going to say head equals new list node. So that's going to allocate us some space. That's memory, okay? That memory has application data in it, and it has a next pointer because that's what's in the list node. But it's garbage. I mean, we don't know what was in that memory just before we allocated it, and so we can't count on it being zeroed out or anything. So it's got garbage in it. Then the next thing we're going to do is we're going to set head arrow next equal to null. So that puts a null in the next pointer, and that means that our node isn't pointing off at some garbage memory location or some other crap, okay? Then we need to move the data in. So we say head arrow data is equal to our new data. So that's going to invoke the copy constructor for the application data class, whatever that app data is. In this case, it's a string, so there'd be a string copy and an altitude that is an integer. And so that would just be, you know, a copy over the numeric value, the integer value. And so we rely on actually, no, that's not the copy constructor. That's the assignment operator overload. And so we're relying on that assignment operator overload to do that stuff for us. Okay. And as long as we've set that up correctly in the application data class, or I think I was calling it list item type class, then we're going to be fine. Okay. And so that assignment operator, this assignment operator overloaded, does this work for us, okay? So that's our first piece of code, is just the body of that if statement. So now we're going to drop into the else of that if. So the else of the if is empty. And in this else, we're going to start off by just doing a search. So we're going to take our test pointer. So this is a pointer to a list node. And the prev pointer, that's a pointer to a list node as well. And those are both locally declared in the insertion method, in the insertion function. So test is being set equal to head. Prev is being set equal to null, okay? And then we start a while loop. And the while loop relies on the short circuiting of the AND. So if this is false, if the test not equaling to null is false, then it won't check test arrow data less than new data, okay? Let me think about this for a second. I'm not sure I set up that conditional correctly. If test arrow data is less than new data. Nope, I set it up correctly. I'm fine. It's fine. Okay, so so the body of this while is pretty simple. Move prev to where test is, and then move test one deeper into the list. So they're going to walk down, one, prev trailing test. Okay. So once this while loop stops, prev and test are going to have some values. Now this while loop may not have ran at all. It may have failed the test arrow data less than new data right off the bat. Okay. That would be insertion before the head. It may have walked all the way to the end and failed on the test not equal to null. And so that's the insertion after the end case. And then we've got the normal case, which means we did walk a little bit of the way through the list, but then eventually that test arrow data less than new data became false and we dropped out. So here we go. We're going to do after the end case first. Now, if we go back to what I had laid out for order before, okay, you search. If test is null, that's the after the end case. So that's what we need to do here. If test is equal to null, okay, so we're set up like this. So, let's say we just have Dallas in here, and we have new data that is Syracuse. Syracuse definitely comes after Dallas. Now this is this is kind of weird because there's only one node in the list, but I can tell you, if you don't get this after and before case is correct, then you won't be able to insert a second node into the list, because the second node in any list, you've inserted the first node, the second node into any list is either going to be before the head or after the end. It's going to be one of those special cases. So I'm just using this single node list to illustrate after the end. So indeed, test has walked off the end of the list. Previous is still pointing to the last node in the list. And so test is indeed equal to null. So we're going to allocate a new list node into test. Again, that memory allocation has garbage in it. We don't know what is in that memory, but it's garbage, okay? We don't know what it is. So we get this new memory. It's hanging off of test right now. Test is pointing to it. And now we're going to say test arrow next equals null, okay? I like to do my pointers first and then the application data, just simply because it's the way I've always done it. So in this case, I'm going to set the next equal to null. And now I've got to go back and point previous's next pointer to test. So I do that, previous arrow next equals test. And so see what happens there? We've got a null in previous because we walked off the end. So that, or in previous next, excuse me. So previous arrow next is null. And so the first thing we do here, or the next thing we do here, is previous arrow next equals test. So that takes test's address and copies it into here. Okay. So I fixed up my pointers. My pointers are all fine right now. The only thing I have left to do is copy that data in. So test arrow data is equal to the new data. So that copies, string copies Syracuse over and copies in the altitude, which is 578 feet above sea level. So again, we're relying on that overloaded operator for the application data class, whatever that is, list item type or app data or whatever it's called, okay? So that's that case. The next case, so this again is an else. So we did else if, or not else. The first one we did if test is null, right here. So I'm going back through the slides. So remember, this is the after the end case. If test is null, we allocate space, we set its pointer to null, we point the previous at it, we copy over the data. Now we're into before the head. And before the head, that's the second case that we're handling after the while loop. And that's in an else. So else if previous equals null. Okay, so our new data that's coming in is Atlanta at 203 feet above sea level. That while loop stopped because test arrow data, that is Dallas, was not less than the new data, which is Atlanta. So we're inserting in front of the head. Okay, so again, we're going to take a few steps here. We've got to allocate space. And so we do that by saying prev equals new list node. That new space has garbage in it. Okay. And we take care of the pointers. So previous arrow next is equal to head. Could have set it equal to test because both head and test have the same address in them. So there's previous arrow next equals head. That's fine. Copy the data in. So previous arrow data equals new data. And then remember I said we have to make sure we update head correctly. So head has to be moved because Atlanta is now the new head. Atlanta is the first item in the list. And so head has to be set equal to the address that previous has in it, which is the address of the node for Atlanta. And so head equals previous fixes that up. And we're done. That case is done. Now we only have our normal case left. So the normal case, this is just an else, okay? So we had if test is equal to null, else if previous is equal to null, else, now we're in the normal case. So we've got our new data, Detroit. We've, the while loop has kicked us out where test is pointed to Syracuse and previous is pointed to Dallas. And sure enough, Detroit goes right in between those two. So we're going to allocate some space. Previous arrow next equals new list node. So this breaks previous arrow next pointing at Syracuse, but that's okay because test is pointing at Syracuse as well. So we haven't lost anything. We didn't lose memory. We didn't leak memory, okay? So the first thing I'm going to do here is I'm just going to redraw things a little bit so that it looks linear again. So So from here to here, I've just redrawn. I haven't done any code, nothing. This is just the illustration. So the next thing we need to do is move previous. So remember, one slide ago, previous was here. Now I'm moving it up to here. Previous equals previous, arrow next. That just makes it easier to copy data and fix up the pointers and that kind of stuff. So we've moved previous to that newly allocated space. We set previous arrow next equal to test. So that links the new memory into the linked list. So now all we have to do is copy over that new data from that was passed in. That's Detroit and 672. And so previous arrow data equals new data, copies that in, and that's it. We are done with insertion. Now, I still have plenty of time left, I do believe, on this meeting or on this lecture. Now, I want to point out that in the book uses temp pointer and after me arrow link. I don't know what the heck he's doing in here. It's kind of weird. At the same time, he has all of these pieces of insertion broken out into separate functions. So he's got a function for searching. He's got a function for inserting before the head. He's got a function for inserting in the middle. And so this is a very particularly object-oriented, wasteful way of doing things. I just use a single insertion routine. That's it. In fact, the way this book is written, it's written much more like the way you would do things in Java than the way you do things in C++. So, just to solidify what we're doing, I'm going to reshare those slides and I'm going to go through them once more, because if you don't get insertion right, you can't get deletion right, or excuse me, removal right, because removing something from a list means you have to build the list in the first place. Okay. So I'm going to go back. We're going to start this from the beginning and we're going to walk through it again. And this time it's going to be a little quicker. So remember, we're doing linked list insertion. So every case, all the different cases have to have specific code for the case. So, so each case is going to be decoded by an if or an else if, or just an else. And the order of the cases is important, so we need to establish that order. Okay, and off we go. We've got normal, which is in the middle of the list. We've got the empty list. It's the first thing in. We've got inserting before the head. We've got insertion after the end of the list. And we've got a duplicate key value that we are not worrying about. I have written the code so that our insertion does not worry about the duplicate key value. And that's just simply because we would have to know what the application is, and we don't. We're the programmer for the data structure, not the programmer for the application. Okay, so we're going to ignore that. Our order basically means that normal, before the head, and after the end all require us to have comparisons to data that's already in the list. And if the list is empty, there is no data already in the list. And so that means that obviously the empty list case has to go first. And that happens before we try to do any searching of the list or anything like that. So the empty list case goes first. Well then, normal, before the head, and after the end have to have a search, a while loop, search through the list to look for the insertion point. And that's using the data that needs to be inserted and the data that's already in the list. And so all of those have to come after a while loop. And so we're going to have an else on that first if, and that's going to have a while loop in it. Okay, so once the while loop finishes, we've got one of three cases. We either found a node whose data is greater than the data to be inserted, or we've walked off the end of the list. Now, that node whose data is greater than the data to be inserted could be the node pointed to by head. It could be that first node in the list, and that would be insertion before the head. Or it could be in the middle of the list, and that would be the normal case. But after the end is the only time that the test pointer is going to be off the end or null. So since test is going to be null, we should handle that case first. So we're going to ask if test is null first. Provided test isn't null, then we either have a normal case in the middle of the list or we have a case for before the head. Before the head has two different ways we could check. I could ask if test is equal to head, or I could ask if previous is null. Well, I'm going to use the second of those two, if previous is null. It seems cleaner to me. Don't know why. You could use the other one if you wanted. Okay, so now our order's complete. We knew that that we had to check this before the head, because again, that previous being null means we can't use it in the insertion in the, you know, as if it's a normal case insertion. So we've got to determine if it's before the head before doing the normal. So indeed, here's our final order. If it's an empty list, then we have the code for the empty, for insertion into the empty. Else, we're going to search with a while loop. And after the while loop is done, we ask ourselves, is test equal to null? And then we have the code for that. Else if previous is equal to null, and then we have the code for that. And then else, and everything else is a normal case. So it's just going to drop into the normal case on the else. Okay, so the empty case, head is equal to null. We've got new data to insert. It doesn't matter what that data is. Head is null, which means if is empty is true. And so that's the body of this if is empty is going to be pretty straightforward. Head equals a new list node. Head arrow next equals null. And then head arrow data equals new data. And we're done. You know, 3 statements, and that's it. We're done. Okay, so that's the empty case. The next thing, so if it's not empty, we have to do a search. And that search, so this is the else of the if is empty. So the search is pretty simple. We have 2 locally declared pointers to list nodes. One is test and one is previous. Test is set equal to head, previous is set equal to null. This sets up the while loop. And then our while loop conditional is while test does not equal null and test arrow data is less than the data we're inserting, the new data. And as long as those are both true, remember an AND requires both of them to be true, then we're just going to walk those 2 pointers down. Previous is going to shadow test. And so remember the first time through test is head, previous is null. So the first time through we set prev equal to test. and test equal to test arrow next. This while loop may not run at all. We might start with test arrow data, which is originally head, being less than new data, and that would be one of our special cases. This while loop might run completely and walk test off the end of the list, so therefore it gets kicked out because test equals null. Or it could have walked part of the way down the list and been kicked out by test arrow data is less than new data, somewhere in the middle of the list, okay? So if it doesn't run at all, previous is going to be left equal to null. If it runs off the end of the list, test is going to be set equal to test arrow next of the last node, and that's going to be null, so that'll kick us out. Or it's just in the middle. So let's do that after the end case first. So test is null. So if test is equal to null, we're going to allocate some space, and we'll allocate that space into test. So test equals new list node. Great. So now we've got some space. That space has some garbage in it. So we're going to fix up that garbage. The first thing we're going to fix up is the pointer. So test arrow next equals null. The next thing we want to do is link this node onto the list, and that requires previous arrow next to be pointing at this new space. So previous arrow next equals test. That copies that address over. And then test arrow data equals new data, copies the data in, and we're done. So that's our after the end case. The next one is the before the head case. So the before the head case falls into the else of the if test is equal to null. And so the else asks if prev is equal to null. If prev is indeed equal to null, then we are inserting before anything else in the list. And that's the case when we want to insert Atlanta, because Atlanta is alphabetically before Dallas. So the while loop doesn't run at all. We end up with prev equaling null. And so this is pretty simple. We need to allocate some space into prev. So prev is equal to a new list node. That space comes, the memory has garbage in it. So we're going to fix up the pointer, prev arrow next equaling head. That points this new node at the start of the old list. So the former list, which had head pointing at Dallas, still does, it's still there, but this previous is pointing to new space, and the new space is going to become the first node in the list, okay? So then we copy over the data, prev arrow data is equal to new data, and then we've got to fix head, because head has to move back, so it's pointing at Atlanta. Fortunately, previous is exactly that address we need, so all we have to do is say head equals previous. Fixes it up, and we're out. And then last but not least, we have our normal case. And so the normal case, we've walked previous and test down the list, found an insertion spot, and it's in the middle of the list. So in this case, previous is pointing to Dallas, which is alphabetically less than Detroit, and test is pointing to Syracuse, which is alphabetically after Detroit. So remember that conditional test arrow data, that's Syracuse, is not less than new data, which is Detroit. And so that stopped the while loop. We're going to need to allocate some space. We're going to need to move some pointers around, and we're going to need to move data into the new space. So we're going to allocate into prev arrow next. We've got previous. We can break, previous and test point to two consecutive nodes. We're inserting right in between those two. And so we can break that link from previous to test because we still have test sitting out there. We still have that address. So we allocate that space. It's got some garbage in it, both garbage for the application data and garbage for the next pointer. I'm going to redraw things here so that it's a little cleaner and it's a little more obvious what has happened here. I'm then going to move previous just simply because if I don't move previous, I'm going to start saying things like previous arrow next is equal to test. Well, double indirection like that starts getting really confusing. It's easier just to move previous. So I move previous by saying previous equals previous arrow next. That moves previous down. It moves it to the newly allocated space, right? So I just took the memory out of its next, which was right here, and copied it into it. And so, or the address. And so now it's pointing here. I'm going to fix up its next pointer. So previous arrow next is equal to test. So everything's linked in now. The structure of the list is fine. The only thing that's a problem is that we don't have our new data in there. And so previous arrow data equals new data copies that new data in, and that's our normal case. That is everything. So there's a reason I went through the slides twice, okay? Insertion is critical. If you don't get insertion right, then you can't get removal right, you can't get searching right, you can't, you got to be able to build the list. If you can't build a list, then you can't do anything else. And so I really wanted to hammer on insertion today. This is your insertion routine. This is the code that you're going to need. You just have to stitch that code together. It's already there. It's already in the proper order. So that's your insertion. That while loop that we use to search with, we're going to use very, very, very similar while loops in both the removal and the search methods. So that while loop is going to get used again and again, okay? That's it for today. So thus finishes the first lecture of our 4th week of online lectures. Please stay engaged. Please watch the lectures, and please contact me if you're struggling. You are going to struggle. Last week, Tuesday morning, 8 a.m., we had a department meeting. I told my colleagues, we're all going to hit the wall. And the reason I said that was because I could feel myself already starting to hit the wall. You can only do this for so long. And then the detachment, the isolation, all of that starts to get to you. You, if you haven't already, are going to hit the wall, just like faculty did. I ended up talking to faculty one-on-one or in small groups in the department multiple times last week after that Tuesday morning meeting. Dr. Kipka immediately said, I think I've hit the wall. I knew that I was feeling like I had hit the wall. I talked to Dr. Lindsay and Dr. DeWitt, and both of them hit the wall. Dr. DeWitt this past weekend said, I'm doing nothing. I'm not grading. I'm not reading email. I have to get away from it. It's eating me up. So we're all hitting the wall. You are hitting the wall. If you haven't hit it already, it's just around the corner. And when you do, if you need help, reach out to student services, student life, reach out to your professors, stay engaged with humanity and stay engaged with your classes, okay? I should have just turned back on the video. You get this talking voice and no face, but stay engaged. I hit the wall, and for a couple of days, it was pretty hard for me to stay engaged. Friday was really tough. And I spent a good part of Friday massively angry, just massively angry. And part of that is just being angry at being in my basement all the time, and not being able to go out of the house, not being able to do anything. I've been locked up essentially. We've taken a couple of drives, but I don't get out of the car. So, in essence, I've been locked up for 20, well, I'm recording this Sunday night. By the time you see it, it'll be Monday, and I will have been locked up for 20 days, almost 3 weeks. And I don't see it ending anytime soon because this crap is nasty. It kills people. It kills people fast. It kills people easy. The death rate is only about 3.5%, but that means 3.5% of the confirmed cases die. I have a health condition that makes me more susceptible, puts me in greater danger. That health condition means that in the initial study, the death rate was almost 4 times, it was like 3.5 times higher than the average death rate for everybody. Keep yourself safe. Just talked to my nephew this morning. He's on the recovery side of it. He said the body aches were horrible. The cough and the breathing. He said today was like the first day in 4 or 5 days that he's been able to take a full breath. And he's getting better, which is good, knock on wood. But this stuff hurts. It is nasty. So take care of yourselves. I'll see you tomorrow.